Welcome. What we're going to talk about today is what is a network and some other things. But we are starting off with our CCNA course. We've already talked about getting started and so on and so on. So what we're going to talk about is network fundamentals. This is pretty much the basics of networking that we're about to discuss here. You can go as deep as you want with this information, but whatever you do, don't use only my particular course as a source of information. You can do as much reading as you like on this subject. You can do very little reading on this subject, but either or, make sure that you understand what the fundamentals are. So let's talk about what a network really is. The concept of a network is having two devices communicating in some fashion, either by a wire, wireless, and able to communicate with each other. Because I have PC1 sitting here and PC2 sitting over here, and they're connected by a cable, and they're able to communicate with each other, what does that tell you? They're on a network. That's it. Now, if you read this little thing here, it says the ability to have communication between two or more devices. Now, in this scenario, we have two, so they're networking. Otherwise, if you just have a single PC, he's just a PC. That's it. But if I connect this PC to another PC in some fashion, it becomes part of a network. When you're talking to your friend, your family, boyfriend, girlfriend, you're networking with them. You're communicating with them. Same concept, except we're doing it with machines. It also says these devices can be considered nodes. Now, this is a good thing to know. I don't normally use this term all the time, but I do use it. So the concept of nodes means anything that has the ability to communicate. Now, in our CCNA, we're only going to be dealing with one protocol, our main protocol, to do communication with, and that's IP. Now, if you were doing Novell, you have IPX and so on and so on. And, of course, with Apple, you have Apple Talk. But we're dealing with IP as our means of communication. So that means nodes are devices that communicate between each other using IP. We use a network card to do this communication, which means if you have two PCs sitting here, you're going to take this cable, which we call a network cable for now, and you're going to plug it into the back of this PC and the back of this PC. And the only way to do that is you have to have what is called a NIC card. This is called a network interface card. Horrible writing, I know. Now, this network interface card is designed to move data over wires and communicate with another network card on the other end of that wire. So this is really what's needed in order to get your machines to communicate. So if you have two PCs but they don't have a network card, you're not going to be able to communicate with them. Yes, there's other means of setting up communications, but in our world, in our CCNA world, we need network cards. And that's what we're going to be using. Here's an example of a network. One example would be you making a phone call. You're sitting here in Annapolis, Maryland, and you decide that you want to call your buddy over here in Baltimore, Maryland. And because of that telephone signal is going to go up. Now, of course, I'm talking about a wired telephone service, but it could be wireless. It doesn't really matter. I have wires plugged into it because, we're talking about a wired network. You and I are going to be dealing with wired networks. This is not always CCNA wireless. So everything we're talking about will be physically plugged into something. This telephone company would take that data, send it across the city where it needs to go, and bring it down into this one particular telephone. That telephone will ring. This ringing between these telephones is, think of it as our communication trying to happen. The phone rings, someone runs over to it, picks it up, or your buddy runs over to it and picks it up. And as soon as he picks up that phone, he pretty much completes the communication. That's a good way of saying it. He completes the communication, and now they're able to communicate with each other. Every time he speaks, this person will be able to listen, and vice versa. So in our world, in the CCNA world, we are going to be focusing on one thing. Routers is one. Switches is the other. And our one thing that we're going to be dealing with is getting communication between these devices and making them work. Now you can see these are pictures of the devices that we have. Here's our router at the top, and here's our switch at the bottom. Now a router consists of a few ports. Here's one port that we will plug our network cable in. Here's another one. And here's a couple more. And you can see we have these modules that we can actually just slide things in and out. These cards here, this is a module, this is a module. And then we have a module over here that we can actually slide something in as well. But with your router, these are called fast Ethernet ports or Ethernet ports. I mean, they're called fast Ethernet, but at this point, just realize they're Ethernet ports. So if you're building yourself a network and a lab at home, make sure you get one that has 2 ports. A router that has 2 ports. So your router will have a few interfaces, and we call these interfaces each one of these ports. And really, each one of these ports is nothing but a network card. You will be able to identify a switch by many ports. As you can see, 1, 2, 3, 4, 5, 6. Of course, that would be 12 if we double it. And if we double it again for all these, it'll be 24 ports. So this is a 24 port switch. The nice thing about a switch is I can hook up 24 PCs. And that's pretty nice. So if I had PC 1 and 2 and 3 and 4 plugged into this switch, they will be able to communicate with each other. No problem. Because they're plugged into the same device. Now, if I had a switch sitting over here, that was on a different network, then I would use this router to communicate with a PC sitting on this switch that is on a different network. Now, a different network is defined by the IP addresses that we assign, which we're going to learn later on in the course. We got a lot more to cover before we get into that aspect. But PCs that are sitting on the same network can communicate with them. These networks are not defined by location, but they're defined by the IP addresses that we assign. And again, that's later on in the course. So if a PC is on a different network, we would use a router to allow that communication. So a switch is there to allow communications between devices that are on the same network. And a router is there to allow communication between different networks. Now, one thing you're going to learn about networking is every idea that I give you goes a lot deeper than what I say, and every rule that I give you can be broken in some fashion, in most cases. So what I just explained was a switch is used to communicate with everyone on the same network. Does that mean that I can have a switch, a PCs on different networks on the same switch? Yes, but in our basic understanding of this, what we have now is all this switch is on the same network. And what I mean is on the same network, that means all these PCs sitting on this switch will be in the same network. This switch up here has a PC sitting on a different network. And if I need to communicate with this PC and these PCs, I will use a router. Now, the interesting thing about a router is, as you see, I'm plugging my router into this switch up here, and I'm going to plug my router into this switch right here. We'll say this is network A, and this is network B. A router can only have one interface in each network. Again, these networks now are what you define, by the way. You're configuring these ports to be in those networks. So if all these PCs were in network A, and this PC was in network B, I will use a router for them to communicate. Now, does that mean can I have a 6 PC sitting over here, and he was on network B? Would I have to go through the router for this to happen? Yeah, you would. You would still need a router to make this happen, even though it's sitting on the same switch. And again, that's way later down the road. Just want to kind of get some of those questions out of the way right off the bat. But for now, we're trying to learn the basics, so don't try to think too difficult about it or too deep. Just remember a router's job. A router's job is so it can communicate and send traffic from one network to another. That is his job.
And orbiting it.
So we just sit and stare.
Now we go back over to here and take a look at this phone company here. We'll realize that Annapolis might have a 301 extension. Now, the 301 will say 555, just like they do in the movies, 1111. And this one has a 410, 555, 2222. Now, the area code pretty much states who's in our same network. Now, I'm not saying this is 100% accurate. I'm just telling you this gives you an idea. That's why we call it an area code. Because this pretty much tells our telephone switching company, where do you want to send that data? Now, if you put in the wrong area code, it's going to send it to the wrong direction. And you might end up getting 555-1111 that's not in Baltimore when you're calling from here. Because this person is calling over to here to get to you, or Baltimore is calling over to here. And if Baltimore doesn't use the 301 extension or 301 area code, that data is going to be sent somewhere else. So you can think of this being the 301 path from the telephone company. Over here might be 516 area code going in that direction. So if you accidentally dial this number as 516-555-1111, your phone call could be completed, but you're going in the wrong direction. So just like our routers, each one of them has their own interface. And each one of those interfaces must be on a different network. But this is an idea what your routers will look like and what your switches will look like. Now let's talk about an interesting thing, which is called connection types. Or I should say connections and types. When we look at these, we're talking about what we were talking about before, which are interfaces. There's several different types of interfaces. Here's a fast Ethernet interface, or the Ethernet interface that we were talking about before. Here's an interesting one, which is a serial connection. Now, usually serial connections go wide range. They usually go in a long direction. You can have serial connections locally, but normally locally we want high speed, as fast as possible. So we would use our Ethernet or our fast Ethernet connections to get that high data transfer between each other. And serial connections we would use to have long distance connections. Now, in today's world, we have some pretty fast wide area connections. But for your studies, you're going to be learning about serial connections and Ethernet connections. In the book, you're going to be learning about fiber as well. Now, these little devices are called SFPs, which are small form factors. And this is where your fiber cable plugs into here. What you'll have is you'll have one of these that are actually glowing red. This means that this particular side is sending data out this port. And this one's not going to have anything because the cable that's plugging into it, like so, is going to be sending the data in that direction, which means this one will be receiving the data, where this one has another cable coming out and the data will be moving in this direction. And that's the basics of how fiber really works, as far as transmit and receive is concerned. These cables are used to plug in different types of connections as well. So as you can see, this cable here, this is what we call a DCE to DTE cable. This will plug in one side of the serial connection, and this will plug into the other side of the serial interface down the way. These type of cables will be used to plug into this type of card. This is called a WIC 1T card. And if we go back to here, that card will fit in one of these modules sitting here. So imagine just unscrewing this, and just pulling this out and putting our serial card right in there. And then we will have not this type of connection, but we will have a serial connection, a serial interface. And when we boot up our router, you will see the serial interface. This little card here, because notice this one only has one adapter for you to actually plug your cable into, which means this will give you one serial interface. This one here has two serial interfaces. There's one, and there's two. That's pretty nice because then when you take this little smaller one, you can push that in the actual module like you would this card, and then you will have two serial interfaces. And this one right here will be the cable that you use. These are called WIC 2T cards. So different type of interfaces are used to transmit your data from one side to the other. Obviously, if you're going to be using a serial cable on one side to plug into router 1, let's say you have router 1 sitting here and you have router 2 sitting over here. If this is a serial cable, you're not going to plug it into an Ethernet cable over here. You're going to plug it into what? A serial connection. Obviously, if I'm using fast Ethernet coming out of here, I'm not going to plug it into a serial connection over here. I'm going to plug it into a fast Ethernet connection. So each one of these, like a fast Ethernet cable, will have eight wires. So here's wire 1, 2, 3, 4, 5, 6, 7, 8. someone has to do the transmitting. We'll have two cables that transmit, and then we'll have two cables that receive. So this is what we call a pinout. We call this a pinout because of the fact that we are using certain cables that are you doing the transmission and the receiving. We also have different type of voltage for this particular Ethernet. So you don't want to try to get the plug into a serial, or I'm sorry, plug into a fast Ethernet connection and then try to change the pins and coming over here into a serial connection and try to make it work. You might be sending too much voltage into this card, or vice versa, and destroy the card or the interface. So if you have a WIC 1T on one side, obviously you're going to have a WIC 1T on the other side. If you have a WIC 2T on one side, obviously you're going to have a WIC 2T on the other side. As of now, if you want to actually find the adapters that go from a WIC, the adapters or the cables that go from a WIC 2T to a WIC 1T, that's fine. But for now, just think of it as serial in, serial on the other end. Think of it like that. And these are just different types of actual cables and modules that you're going to use and interfaces that you're going to use. Most likely, you're going to be using these or this one and fast Ethernet. Now, your console cable is really important too, because this is the console port used by this console cable. It's what is extremely important for you to be able to log into the back of your devices. Every device is going to have a console port, and you need to plug into that console port in order to log into the device and get the information you want out of that device. And when I say information, it's more than just information. You're going to be using that as a means of making those routers and switches do exactly what you want. So our network devices also have these symbols that we kind of are going to start getting used to. As you notice, I was drawing a router. I drew a circle for a router. And I put an R in there, and then I'll have the router 1. If I'm connected to another router, I'll have a router 2. If I draw this symbol here, as you can see, here's my router. If I drew this symbol here, that means I'm using a serial connection, as you can see with the lightning bolt here. If I was going to connect to another router, say router 3, and drew a straight line, that means I will be using an Ethernet connection. So what does that mean? Obviously, if I have a lightning bolt, I'm using a serial connection, which means I'm going to be plugged into what? A serial port on this end and this end. If I have a straight line, that means I'm using Ethernet, so that means I'm going to be plugged into what? An Ethernet or a fast Ethernet connection. These are just names that you haven't really learned what they are just yet, but doesn't matter. You know now if I say, hey, I got a serial connection, you're going to know, okay, well, if I have a serial connection, that means I'm going to need a serial cable and obviously a serial port to plug into it. And if my router doesn't have a serial port, guess what? I can't have a serial connection. If the router only has one fast Ethernet connection or a port on its router, that means I only can have one other router plugged into me via Ethernet. Now, if I decide to plug router 1 into a switch, notice my square here is a switch. I would also give it a name like this, saying switch 1. And I would draw a straight line or a line like this, which is still a straight line. This is telling me that I have fast Ethernet here plugged in, fast Ethernet plugged in here. Now, your switches are always going to be fast Ethernet. So that means in order for me to plug a router into a switch, it can never be something like this. because switches don't have serial ports like that. Okay, does that make sense? Hub is something we're going to talk about, but not something that you're going to be using. If I was actually drawing out a hub, I would literally have this, and I would say hub 1. That's how I draw them. And eventually we'll be talking about hubs. But most of you will not need to have a hub in your lab. Put it to you like that. You will not need it. But we will be discussing how traffic moves across a hub. And of course, hubs are only Ethernet ports as well. Firewalls, never really in my course with CCNA. So you won't see those here. The bus, we'll talk about the bus a little bit, but not to the point of really needing, we're not going to be using it. And here's the cloud. The cloud we will be using as well. So let's talk about two things that, and also here's a bridge. We're not gonna be talking about bridges either. I mean, might have some, talk about some things about bridges, and that might not even happen either. But we will not. You will not see me be drawing this. These are the symbols you'll see me using all the time: Ethernet, router, switch, serial connection, and cloud. So let's talk about this idea of the cloud. A cloud usually symbolizes that we have a router that's plugged into a cloud, and over here is another router that's plugged into the cloud. Which means that this normally when you see this means we have either two routers sitting at the same site going into the internet, and we don't have any other, and no other idea where that traffic is going. We just know it's going to the internet. Or we have multiple sites that are going from one side to the other. So if I'm sitting here in Texas with a site and sitting over here in Maryland, over here at this particular site, this router belongs to me in my Texas site, right here, and this router belongs to me in my Maryland site. We control what? The router and this interface sitting on the router. We control this router and this interface going to this router. On the other side is a router that belongs to whatever ISP that we're using. We have no control with these routers, nor do we know how many routers and switches are in between to get from Texas to Maryland. We don't know, and the most important thing is we don't care. We really don't care how that traffic gets from this spot here over to this spot in this direction. No idea, and we don't care. So this is what the cloud symbolizes. It symbolizes that we don't really know what's going on in here. So we make this cloud idea, the idea that we can't really see through a cloud. And that's the concept of the cloud. So you will see that a lot. But in most cases, it's going to be site to site like this. Or both of these could be Maryland sitting in the same building. So that means both of these routers are sitting right here, plugged into a switch here, plugged into the same switch. And what we're symbolizing here is the fact that we're at the same site, same building. We got redundant routers. We got two routers to move our traffic. And this traffic these routers are hitting the internet. We have no idea. We don't have any other sites. And we might even set this up like this and have another router up here. Router 3, which is in Texas. So that means we have site-to-site communication from Texas and Maryland, and our Maryland site has two routers going to the internet, where this router has one router going to the internet. But when you usually have this type of setup, we say it's going to the internet, but we're really not trying to communicate with internet traffic per se. In our world, and when I say our world, I mean the network guy or the network girl or the network man and network woman, they will be considered with the communication between this router and this router. We call it site-to-site communication because you're trying to communicate with your Maryland site and your Texas site. Now, let's talk about what we call a logical diagram. This is very important because you won't see me do this often, but you'll see documentation do it. So, if I have a router and it's plugged into a switch, and I have another router that's plugged into this switch here, and let's say I have a PC sitting here, and let's say I have another router sitting over here, and he is coming into a switch, and here's a PC sitting here. These switches are normally means that we actually have this interface, and this interface on the same network. Now, when I mean interface, obviously the interface is sitting on the PC. But you also have it plugged into a switch interface, so I just put it right here in the middle. Same thing here. I mean, we got two interfaces here between each link. So if this means ideally that they're on the same network, instead of drawing out the switch, sometimes what they'll do is this. We'll have a line drawn like this. And then we'll have a line drawn out like this. So you'll see this a lot. What this means, we call this... Now, when you say a lot, you won't see it a lot in my course, but you will see it a lot in documentation. We call this a segment. So think of this segment as a network A, network B type thing. Everyone on this is on the same segment, which means they're on the same network, which means they're plugged in physically to the same switch in some fashion. Because this is our logical diagram in that fashion. Now you're asking me right now, well, why would you do that? Why not just draw the switch? Okay, so let's say you're plugged into here, you're plugged into here, and you're plugged into here. And these switches are plugged together. Would you want to draw out switch 2 and switch 3 and switch 1 every time? And all these are on the same network. There'd be no need to. So to make it simple, I can just say router 1, router 2, PC 1, here's the cloud. We can have this router go out, this router go out, and everyone is on this segment here. Okay? It makes it easier for my diagram. I know for a fact that all these are on the same segment. It gets some getting used to, but ideally, this PC is not just plugged into some line that's going across. It has to be plugged into something. And what do you think it's plugged into? A switch. I mean, that's it. In order to get more than two devices connected on together, we have to have it on some type of device, right? And that would have to be a switch. So those are things that I really wanted to bring to attention. You will see that in your documentation. Most likely you will not see that in my course at all, but it's possible. So these network symbols are something you need to get used to. Just keep, just eventually they'll come to you. But the router, the switch, the cloud, the serial connection, Ethernet connection means something. When I draw those symbols, it means something. You know how I'm connecting them. So how do we fit all these things together? Now notice, whenever I want to hook up multiple devices, more than two, I'm going to have a switch. All of them are connected to a switch. This allows PC 8, 5, I think I got 8 in there twice, so that might be 6, but either or. And 7, I think that's 6. PC 6, 5, 6, 7, and 8. It allows all of these PCs to communicate with each other. It also allows them to communicate over here with network A. Why? Well, let's talk about that. If this router wasn't here, and this is the only connection that we had, that means even this wire is not there, PC 5, 6, 7, and 8 can communicate with each other. But they can't go any farther. So that means if I wanted PC 1, 2, 3, and 4 to communicate with these devices, I would have to plug them up to this switch somehow. Then all of them can communicate. But what if I didn't want them all on the same network? What if I want them all, what if I wanted PC 1, 2, 3, and 4 on a different network? Well, I would come over to here, put them on a different switch. Doesn't mean you always have to do it that way, but in our example, we have a different switch that we plug these devices up to, and we're going to add an interesting thing called a router. What's a router's job? Its job is to send traffic from one network to another. That's the job of a router. So here's router 1 sitting here. Now this particular interface is going to be configured for network B. And this interface over here is going to be configured for network A. And the router's job is to send traffic from one network to another. Now remember, a router can only have one interface in a particular network. So if network B is on this particular interface, I cannot have another interface that belongs to network B. And again, these networks are defined by an IP address. So if I have an IP address of 192.168.1.x, and over here 192.168.2.x, because the way I assign these IP addresses, they're on two different networks. They will not be able to communicate with each other, which means if I had all these PCs sitting on this switch and I gave it an IP address of 1.x and gave it of 2.x, which would be 192.168.1.x and 192.168.2.x, these two PCs, even though they're sitting on the same switch, will not be able to communicate with each other. It won't happen. That's TCP IP doing its job. It will not allow that communication. But in our example here, I got them on two separate networks. I got to have a interface of that router on network B. I have to give it an IP address that belongs to network B and plug it into the same switch as the other devices are sitting on. Same thing for network A. If I had network A, or an interface on router 1 with network A, it would plug into the same switch as the other PCs will plug into. So when any of these PCs need to communicate with network A, it will send that traffic. Let's say PC8. PC8 says, hey, I'm trying to communicate with network A. Guess who he's going to send it to? He's going to say, I'm going to send it to router 1. Because router 1 does the communication between networks. And network A isn't on my network. So I know I have to send the traffic to the router. The router looks at it and says, oh, you're trying to get to network A? Hey, I'll take care of that. And I'll send it right on into the switch. And that traffic will find its way where it needs to go over here to PC3. And this is how all our devices fit together. This is the basics. Now, at any given moment, you can have yourself a firewall here. And you can slide that bad boy here. Which means that anytime traffic is going out of this router into this network, it has to go through this firewall. And this firewall gets to decide what traffic is allowed, what traffic is not. Again, that's just something I added. It's not really necessary, but it's good to know. Because as network guys, it's very easy to forget about firewalls. Very easy to forget. And I mean very easy. So technically we already talked about the purpose of the switch. And that purpose is for us to have multiple PCs to communicate with each other. If this was a 24-port switch, we will be able to have 24 PCs plugged into this switch. Now, once you do that, though, you have no more spots. Which means if I had 24 ports all used up, there's no way these PCs will be able to communicate with any other network because you would need a router to plug into this switch. And guess what? A router takes up a port. Now, if that router takes up a port, how would I fix that problem then? Well, that means I would actually have to get another switch, plug that switch into this, plug that 24th PC into here, PC 24, plug it into here, and there we go. So now this will be port 24 on this switch. This will be whatever port you want, whatever port you want. That's what I will have to do. I'll have to add another switch to make this happen. And that's the nice thing about it, because we can add switches and connect them together, and we can turn our 24-port capability into 48 ports. Isn't that nice? Anytime we want more PCs, we just add another switch, switch 2, and connect it to switch 1. And now you have how many connections? Like I said before, you're going to be using one up for the switch. You're going to be using one for this switch. And you're going to lose one for the extra PC that goes in there if this was already filled up. But that still gives you 22 extra ports. After you've removed this off of this switch, plugged it into the new one, and connect the switch up. So the purpose of a switch is to give us many possible connections. Now the switch does a lot more than that, which is what we're going to find out later on, but for this purpose, this is the idea of the purpose of the switch. So you as a green person, which means you're green, you're brand new, you're a novice, you're a newbie, and I tell you to go pick up a switch out of the closet, maybe in storage, please go pick up a switch, you know that a switch is something that needs to connect many ports together. You're going to be picking up the one that has lots of ports. You're not going to be picking up the one that has one or two ports, because most likely that would be the router. So let's see how all this fits in even more. Now this concept, what we have here, notice how we have a drawing, a network diagram, starting from here. Here's PC1. Now, think of your home. You have a PC, you plug it into the switch 1. That switch plugs into it, also has a router plugged into it. Now, in your scenario, you're going to have a switch/router, which means instead of having two separate devices, your CCNA is always going to be two separate devices. You're going to have a router and a switch. They're going to be separate. But your Linksys device, your Fios device, your Comcast device, your Cox Communication device, your Sprint device, whoever you're getting internet service from in your home is most likely going to be this kind of device sitting here with antennas coming off of it, and it's probably going to have these switch ports on the side, probably 4 switch ports. And that's pretty much it. You're going to have the cable, and you're also going to have this WAN port. We'll call that the WAN, W-A-N. Okay, and that plugs into your, whoever's providing you your connection. Now, let's say it's Comcast. So we would draw this cloud and write Comcast in it. So we know that this is our WAN port, that this connection is coming from Comcast. We care about this port that's sitting in our house, but after it leaves this wire, we don't care where it goes and how it gets there. We don't have an idea, and we don't want to have an idea. We don't care. Now, these extra 4 ports, or 3 ports, let's make another one here. These extra 4 ports just gives you the ability to plug things in. But most of you guys will use the wireless section of it. These are your switch ports. And the box is the router itself. So it's a router / switch. Okay? Now, as this PC, which is PC1, he's going to send communication and try to talk to PC2. Now, because they are on the same network, or the printer here, are on the same network, that traffic is going to go up, hit the switch, come back down. If he's communicating with the printer, it's going to come up and come back over here. And the router was never concerned with the traffic, and the router would never get the traffic. But if PC1 wants to go out and hit the internet, you're going to type in www.yahoo.com. But remember, you might be typing that in, but it is getting resolved to a IP address. You might be putting names into your browser, but that name is being translated to an IP address. Your PC would do this. It's like, look, I'm trying to communicate with www.yahoo.com. It'll look up the actual host name, which will be yahoo.com, and find out what the IP address of Yahoo is. Then he will actually send the information out to the IP address. Let's say it's 1.1.1.1 is for Yahoo. And the PC is going to look at it and say, well, wait a minute, 1.1.1.1 is not on my network. So where will PC1 send it? The only place where that can send traffic between networks. They'll send it right to the router. The router will get that information and says, "Oh, you're trying to get to 1.1.1.1. Okay, I know it. I know for that traffic, it needs to go out this interface here, and send it out to the cloud, to Comcast. Comcast will hand it off, and the data will go from there. And you would figure, well, that's a lot of steps for this to go. There's a lot more steps than that, and you still get your web page really fast. So with this, all this stuff sitting at this router and below is called a small office home office. Now, as a network engineer, most likely you will never set one of these up. As a PC guy goes around and fix people's PCs, he would set these up, but not in the fashion that you would. I mean, he would go out and get a Linksys router, because that's what I used to do back in the 90s. I would go out and buy them these Linksys routers, thinking that I was good at networking. I didn't really understand what networking was until I started getting into CCNA training. And boy, it's a magical world. But this small office, home office, some large enterprise networks, you have VPs or people who work from home, and they're going to have a router, but they're still not going to have that Linksys router. You're going to take a real router, like a 2800 or a 2900 or a 1900. It's most likely going to be the 19 series or the 18 series, and you're literally going to have a router and a switch and PCs and printers plugged into those switches like this, just like this. This will be the concept of a small office, home office. We say that because of the fact that small offices will have this type of setup as well. Now, don't get me wrong. This concept of a router hooked into a switch is what we base all our training on. But the reason why SOHO is important is just the fact that we understand that it's small. Is it really important for you to understand this? It's just a term that's in the book now. That's the only reason why I brought it up. That's it. But you need your switches to communicate between each other, and you need a router to get out of that network to go somewhere else. So this will kind of be your design. In most cases, I'm going to have a PC, I'm going to have a switch, I'm going to have a router. So, I said several times the concept of Ethernet. And this is what we're going to discuss in our next section. Because the network fundamentals, Ethernet does have a part of this. In fact, you know what? No, we're gonna continue on, because actually all this is network fundamentals. So we're not gonna end right here. I was thinking about making this a second chapter, but there's no point. So, Ethernet. Let's talk about that. Ethernet is the means of how data is moved across a media. What is a media? When you had your beautiful tapes here, okay, what is this? This is kind of like your little tape that you used to put your music on. This is a media. Then things got fancy and we got to CD-ROMs. This is a media. But even before our tapes, what did we have? We had records. And then we got from CDs, and then we got to what? Big old laser disc, right? We got a big old laser disc that we could use. And then we got to what? We got to these nice little small, tiny flash drives. And there's lots of different types of medias in there, but these are medias. Okay? It's where our data is stored. But in this concept, media means what are we sending the data across? Because in the networking world, we're not just holding data. We're not storing it. We're sending it. So if I send this over a fiber cable, our media is fiber. If I send it over an Ethernet cable, well, that's funny because we call it Ethernet cables. This becomes a term that we usually, use as a means of saying, okay, we're using a Ethernet cable. But really, it's what we call it is twisted pair cables, or another word would be Cat 5, Cat 6. And of course, you got Cat 5e and Cat 6e, but all it is a cable. That's it. Cat 5 and Cat 6 are twisted pair cables. We call them Ethernet cables because normally we use Cat 5 and Cat 6 to plug into our Ethernet ports. And since we're plugging that cable into our Ethernet port, we are calling it an Ethernet cable. But we don't call it Ethernet fiber, do we? Even though we're running Ethernet over fiber cables. It just happens to be a term that people just started to get used to and just started saying Ethernet cable. But in your world now, in our world now, you're going to start calling them, you can call them Ethernet cables if you want, but you're going to start calling, saying Cat 5 or Cat 6. Definitely understand those terms, which we're going to be talking about those anyway, shortly. So let's talk about what Ethernet is. Let's say your life. Let's say you have a certain rules of life. I'm going to tell you some of my rules. Okay? No killing. This is a general rule for me. I mean, I'm hoping it'll be a general rule for you as well. Okay? And I do not, under no circumstances, affect somebody else's life. I do not affect others. Unless it's in a positive way. Now, this rule kind of makes me kind of annoying because when people are asking me specific questions, if I feel that it will affect you in a way of going in that direction, if I sense that you're not the type of person that will make a judgment call, that you're just going to be using my advice as a means of just getting the answer and just going with it, I won't give you the answer. So people find this very annoying. It's like, just give me the answer. I just want the answer. But remember, these are rules that I want to follow. I choose to follow these rules. Now, these are self-life rules. What about the general life rules? No speeding. That's one. No killing is another one. No fighting, which they call assault. What else? Did I say no? I thought I said no stealing. No stealing. Okay? These are general rules. Now, you can speed anytime you want. You can kill anytime you want. You can fight. You can steal anytime you want. But when you get caught, there are serious consequences. Now, these personal rules, no one's really worrying about them. You can break those anytime, at any given moment, so on and so on and so on. But these general rules, these general life rules, is what we call protocols. Now, these protocols mean something, which means when you're speeding, guess what? You're breaking protocol. You know for a fact that you're not allowed to speed. Really, one of the major ones should be in here is HOV lane, because we know cops love to catch you in the HOV lane. But these are called protocols. When you break these protocols, certain things happen. You get pulled over. And what's the protocol when the lights go on? When a cop is behind you, What is proper protocol? Proper protocol is to pull over. Interesting. We all know this. What is the proper protocol for an ambulance? To pull over. Now, there are people who don't do this. What's the proper protocol for a school bus that actually has its red lights on? Not the yellow lights, but the red lights when they're flashing to stop where you are, even if you're on the other side of the street. Now, this can mean something in a lot of people's mind. These protocols, think about it like this. I'm coming in to my street here. Okay, and then we got houses sitting over here. I was about to draw a PC there. And we got some houses over here. And here's our main street that's coming. Here's our main street. Here's my horrible car. And right here, the bus is sitting. That really should have been the bus. The bus is sitting over here with the lights on. The kids are getting off the bus, walking onto this media, and I'm turning into here. Now, do you know how many people don't stop here? I stop. This is where I stop, right here, if this bus is sitting over here. This is the main road, but this is turning into my community. I will stop right here. I will not pass this bus. Other people just fly on past. To me, my personal protocol means that I'm stopping at this bus. So what am I getting at here? This concept of protocol. Rules. Regulations. There's certain rules that must be followed in order to keep peace, or someone's idea of peace. In order for us to have communication from PC1 over to PC2, guess what we have to have? Some type of rules. Some type of protocols that make sure that when data is leaving this PC and going over to PC2, that this data it maintains its integrity, is sent over there in that actually gets over to the PC2, depending on what type of traffic we have. Because we do have methods of making sure it's guaranteed, and we have methods that make sure that's not guaranteed as well. But at the same time, even if it's not guaranteed, when I send data from this side over to here, I want the data to get there. We have protocols that deal with this. There's lots of different types of protocols that we will use to govern this traffic. Ethernet is one of those protocols. Now, it's not a protocol to the point where we would actually go in and make changes to it. Ethernet is what we like to call a standard. Now, just like I had the list of things here, we know our standard rules. No killing, no stealing, no speeding. We know these general rules. And no fighting, right? All these rules, they're standard, right off the board. I mean, you got two people here ready to scrap and ready to get mad and angry. And what's the first thing that comes to their mind? I'm gonna let him hit the first punch, because if I do, then I'm just defending myself. And they'll find ways of trying to bend these rules in some fashion. They'll find ways of trying to maybe manipulate the situation. But the bottom line is, we all know what these standard rules are. So Ethernet is what we call a standard. a industry standard, which means that if you have a proprietary protocol, you can call it Ethernet all you want. But if it doesn't follow the industry standard by the powers that be, you're not legit. You're not a legit standard. Now that's the interesting thing, because the power that be here will be this IEEE number. So IEEE, so we call it IEEE. And this is the engineering organization that will provide you with a particular number for a particular protocol, which in this case is Ethernet, and give it a certain standard. And standards are nothing but rules. It's like, look, let's think of some standards here. It might say, look, when using Ethernet, all NIC cards must provide 5 volts. But no more. Okay? No more. Let's say greater than. Let's do greater than. No more than 5.2 volts. Right? Or I should have said greater than or less than, shouldn't I? I should have said greater or less than or equal to 5.2 volts. I think that's the right way to write it. But you get the idea. This might be a rule. There might be certain other protocols that are within this saying, look, when data is leaving this PC, we must have this particular information in the actual data. Let's think about that. When PC1 sends information out, it might need certain information in order for PC2 to communicate with it. This way, they're speaking on the same language. So after all this explanation, we know protocols are nothing more but a set of rules. Don't speed, you're breaking protocol. In the military, they'll use this a lot. They call rules protocols. When you're in there and you are being reprimanded for whatever reason, they don't say, well, he broke the rules. They say, you broke protocol. You went out of the lines of the rules that we set for this mission. You broke protocol. There will be some unique protocols and some standard. Ethernet, industry standard, means that everyone who's going to deploy this type of communication must follow these rules. So let's look at some characteristics of Ethernet. Remember, this is not something that you configure. So again, let's think about this. What is Ethernet? Ethernet refers to a family of LAN products. What does LAN stand for? Which is something we're going to be learning here. It's called Local Area Network. So local means anything that's locally to you. So you got your switch and you have your PCs. And in fact, why don't we do it this way? Let's go back to our diagram here. This is considered a LAN. You know why? Because it's local. Local area network. Notice that I have it right here. It's local to you. Now, I don't have the router in there, but technically the router is part of it as well. I should be drawing this way up here. The only reason why I didn't was to show you really that the SOHO is the entire thing and the LAN sits within there. And once we hit the router, we've gone out of the LAN. And we are leaving the LAN going into the wide area network, which is our WAN. So it tells you right here that Ethernet refers to a family of LAN products, which means those LAN products will be rules, regulations, protocols. It defines the carrier sense multiple access. Now this is another protocol that's within Ethernet. And we're going to learn later on what this exactly does. It also tells you it provides MAC addresses. Here's some other things: duplexing, differential services. You don't need to know what these are right now. Flow control. You're going to learn flow control. Duplexing, you'll learn a little bit about. We don't go really in detail. Media cloaking and speed attributes. And that's an interesting thing because data travels at a certain speed. So here is PC1. Here's PC2. This is plugged into this switchboard. This is plugged into here. We're plugging into Ethernet ports. So what does that tell you? It's telling you that we're running Ethernet. So this PC and this PC are communicating with Ethernet with this particular switch. So they plug into these ports. And what happens? You can set the speed on these interfaces, or you can set them to auto. And they will negotiate what the speed is going to be and some other attributes. Notice it says speed attributes. It's more than just how fast the data moves. And Ethernet will be doing this in the background, and all of a sudden your ports come up, and the speed is automatically negotiated. Have you gotten to the point what I'm getting at here? This is nothing more than a protocol. You're not going to really get in detail with this. You're not going to be making changes to this. This is something that just is. But when people talk about Ethernet all the time, you got to know what it is. It's just a standard. That's it. Okay, so let's get farther down here. I was wondering why I wasn't seeing my scroll here, but that's because I didn't have the mouse enabled. So let's simplify all this information. Ethernet is a family of protocol that, one, defines the standards for communication for local area networks. That's it. Wow, well, that's simple. You're telling me Ethernet is nothing more than this underlying thing that's governing communication on a local area network on a LAN? That's it. Ethernet is a family of protocol which travels over particular standardized cables. That's a little confusing. Well, think about it. Ethernet is a standard that is going to be sitting on an Ethernet port. Here's my port. Here's my Ethernet port. I'm going to plug this cable into this port. Okay? And you're going to have your pins coming down here. And this device is going to plug a piece of RJ45 into here. And here's your cable coming out. As these pins are hitting down into this top of this jack here and going across the wires, Ethernet has certain rules and regulations as the voltage, the pulsing that you're sending down. When I say pulsing, this data that's moving around is pulses of electricity. So we can't just flood this thing with data. We can't just move it down. There's certain rules and regulation it has to follow, even bringing the data onto the wire. So that means something, because the network card has this port and has all these circuits on it. If we go back, that's a shame. I thought I had that up there, but I don't. I'm going to have to add that on there. But anyway, even this device here, let's take a look at this one. You see all these circuitry that we have on here? This is what a network card has. All this circuitry. So because of that, this network card is not something that's just simple. That's just doing a simple job. It has a job to do. And Ethernet job is to make sure that this network card is doing its job in a way where things are being sent over the wire correctly. Because we have lots of steps before this information gets turned into electricity and sent on to this cable. So that's really what this means. Yeah, we got data sitting on this PC. We got ones and zeros. Think about it. We got ones and zeros. But we got to take these ones and zeros and we got to turn them into electrical signals. Electricity. That's what we have to turn it into. And Ethernet makes sure that that information on this side is being put on the wire a certain way because it knows on the other end of this cable it's going to be another Ethernet device. And guess what? That Ethernet device is going to need to read the information that's coming across this cable. So don't you think it'd be nice to have another Ethernet port over here that follows the same rules? There you go. Otherwise, if they follow different rules, we have the Wild Wild West, and you have a lot of PCs not being able to communicate. So this is Ethernet in a standard, in a simple form. You can go as deep if you want as Ethernet, but at the same time, I'll leave it to you to make that decision. So now we get to talk about types of Ethernet. Because we might have Ethernet, but it would be nice to have some types of Ethernet that we're going to discuss here. So Ethernet has several types of these different speeds and different distances that we can actually send data across. So when we talk about Ethernet, really, we're talking about 10 megabits per second. This 10 base T. So let's talk about what this means. The 10 is your speed. The base is just telling you, look, this is just 10 base. This is telling you that we can send data up to 10 megabits per second. Now let's talk about this because our megabits per second means something. A bit is either a 1 or a 0. Okay? It's either 1 or a 0. All PCs communicate with 1s and 0s only. The 1 will mean that it's on, the 0 means it's off. It's just a series of possible combinations. So if I have a light switch, let's kind of throw this light bulb here. If I have this light switch here, I will say a button. How about better that? Let's lose a button. Make my drawing a lot easier. If I have this button that I push, let's say this is actually going to ground. I have this power source here. We'll say it's a battery. This will come to my negative. And this will be my positive. And this button is nothing more than a switch. So when I push this button, the power that's normally off turns to on. Well, guess what? When I push it and it's on, it's a 1. If I turn it off, it's a 0. Okay, pretty simple. I have two possible combinations. 1 or 0. Now, if I add another switch or another button here, and flow this through here, and we're going to have two here, and go up through here. Let's think about how this works. And I'm not going to get too technical here. But if I push this button, if this button is on, and this button is on, which means maybe in the down position, because you're pushing a button. If you push it on, it'll actually, the button will be down. And if you push it off, the button will come out. But if I had this on and this on, the light bulb comes off. It will be on. That's a combination. That gives me a 1. If I have this on and this off, then that gives me a 0. That's a second combination. And if I had this off and off, this might be on. And that's a third combination. Does that make sense? Imagine having these buttons as with thousands and millions of possibilities. We call them transistors. Circuitry. Okay? So your output is either going to be a 1 or 0, and we use this ability to give you all the output that we get. All this magic is done by 1s and 0s. So a bit is either a 1 or a 0. You don't need to understand fully the magic. Just understand that a bit is 1 and 0. If I have 4 bits, we call it a nibble, which is most likely you won't be seeing often. If we have 8 bits, we call this a byte. So a byte equals 8 bits. If I say I have 1 byte, that means I have 8 bits. If I say I have 8 bits, that means I have 1 byte. But everything we do in the networking field is bits. Everything is bits. So now, what happens if I have 100 bits? Well, nothing really. But if I have 1,000 bits, that equals a kilobit. Now, this could transfer into bytes as well. If I had 1,000 bytes, it would be a kilobyte. But we're talking about bits. In the networking field, in our world, it's all bits. But for storage, you can look at bytes, gigabytes, terabytes, brontobytes, whatever you want to talk, zettabytes. But here, we're dealing with bits. So we're going to say 1,000 equals a kilobit. That means now I have 1 kilobit. 1 kilobit. Now, if I take 1,000 kilobits, that's going to equal a megabit. You're starting to see what's happening here? So if I take 1,000 megabits, and notice that B is small, then that would equal 1 gigabit. Now, if this was a big B, a capital B, it would be bytes. So if I was over here and I said, okay, I'm going to take 1,000 bytes, that's going to equal 1 megabyte. So this is how we actually identify our information and how much data is actually going from one spot to another. We use this as a means of measurement. I mean, that's really the way we do this, and our measurement is measured as speed. When we say a car is going 60 miles per hour, we're saying about at the speed that is going right now. The speed that we're going right now. I got that all backwards. Give me a second. 60 miles My brain's not working today. 60 miles per hour. We're saying that, look, at the rate this car is going, in an hour's time, it would have gone 60 miles. A lot of people use this as a sense of speed. Oh man, he was flying. He was going 60 miles per hour. But really, it's a term of distance, right? Or is it both? Some scientist says you can't have space without time. You can't have time without space. You can't have time without distance. So space-time is what we want to call it. Same concept here. Here, we're going to say 10 megabits per second. We're not really measuring distance here. We're measuring how much data that we're moving per second. And this relates to us as speed in a lot of fashions because we want to know how fast we're getting our data. I mean, that's really the bottom line, right? So a 10-base system is saying, look, the base of this speed is going to be 10 megabits per second. And that means we are going to be sending this data over twisted pair cable. Now, what does twisted pair cable means? It means that the cables that we're using to send the data over is literally twisted. We have 4 pairs in there, in each pair, or 8 wires, and we twist 2 wires together with so many twists per inch. So if we take a look at this cable here, and look how we're really twisting this cable. This is how it's going to look. Now, this one has so many twists per inch. Same distance cable, but we got a lot more twists per inch. So twisted pair, we literally twist these cables that are inside the jacket. Now, the purpose of this is to eliminate magnetic fields and to lower the power of the magnetic field. This one has more twist than this one that's sitting right next to it. Their magnetic fields will not be able to sync. The twist will do 2 things. One, the twist will lower the magnetic field, will limit it, so instead of being out to here, kind of like out here, it might only be out to here. So it limits our magnetic field. And the reason why we have multiple twists, this one will have different twists per inch than this one, is so these magnetic fields don't kind of like bond up into the same frequency and just become one big magnetic field. That's the whole purpose. Because otherwise you're going to get data corruption as it's going across the wire. This is electricity. Electricity creates a magnetic field as it's going through the cables. Okay? So when we have Ethernet, Ethernet really means that we're doing 10 base T, and it really means that we are doing 10 megabits per second. That's really the concept of Ethernet. So when I say Ethernet, I use it in the terms of just talking about Ethernet itself. We're running it over Ethernet cable, or we're running over Ethernet, which means I'm going to be having Ethernet ports, Ethernet cables, which would be Cat 5 or Cat 6 cable. But really what I should be meaning when I say this is 10 megabits per second. But that's not the case. We use Ethernet interchangeably. Now, if I want to go to fast Ethernet, that's a different story. Now, notice these are my IEEE numbers. You can memorize these if you want. I don't. I don't spend the effort of memorizing all these numbers. And fast Ethernet, and you will actually see on your router, you'll see either Ethernet or fast Ethernet written on your port. When you see it say fast Ethernet, that means that port has the ability to go up to 100 megabits per second. It doesn't mean this is what you're getting consistently. It means it has up to 100 megabits per second. Now I can go up to 1,000 megabits per second or 1 gigabit per second. And I can do the 1 gigabit per second either on twisted pair or fiber. And then, of course, I have up to 10 gigabits per second and 40 gigabits per second. Most likely, yours is only going to be doing 100 megabits per second, which is all you need. I mean, technically, you only need 10 megabits per second for your labs. You don't need speed. I remember sitting there I was actually turning on a clock speed for a router. And I turned it to 64,000. I was like, why would you do that, man? Turn that thing all the way up. I'm like, why, man? Those pings, it doesn't matter if the pings take, they're so fast. I mean, I probably get 5 pings within a second, maybe 2 seconds. I mean, do I want to get it in 0.80 seconds? I mean, does it really matter to me? So I never really cared about the speed. I mean, you could, doesn't really matter. I personally like the lower speed because on the very high speeds, I mean, I could do 10,000 pings like that. I don't want to. I want to be able to send 10,000 pings and have it run long enough for me to be able to make changes on the end if I want to see if it affects my pings. So these are your Ethernet types. And this all depends on the port that you're using and the technology you're using. How do we determine this? Well, obviously by the chipsets that we're using, by the circuitry that we're using, and we give these circuitries names. When you have one flash drive that only has 4 gigs, isn't it different technology when it's the same size flash drive but can do 8 gigs? Well, these would be gigabytes. I mean, same thing, but one's 4 gig and one's 8 gig. It's different technology, and we might call this flash. We might call this fast flash. Make sense? That's what we're doing here. Most likely you'll be dealing with fast Ethernet. The 2950s, those are fast Ethernet. The 3550s, 3560s, those are fast Ethernet. So, but it's nice to know your Ethernet types and that they exist. Now, this one is talking about our cables. Now, remember, we need cables in order to plug our devices in. A lot of people call them Ethernet cables. And whenever we think about Ethernet cables, we have a category type of cable. This is what this cat means. It means category. So if I have a category of 5, that means this is the minimum cable that I need in order to run Ethernet successfully. And you can see I have Cat 1, 2, 3, and you can see they're all for telephone. So it wouldn't be a smart idea to take Ethernet and try to run it over a telephone wire. You might not get guaranteed delivery. You might not get good communication. You might find yourself having all types of weird issues. This would be token ring. Notice that we have Cat E. Cat E gives us the ability where Cat 5 only gives us up to 100 megabits per second. We can go to Cat E and give us 1 gigabits per second. Now, you got to ask yourself, what's really the difference between Cat 5 and Cat E? You really want to know the truth? Really, the main difference is twists per inch. A Cat 5e cable will have more twists per inch. A Cat 5e cable will have more twists per inch. Why? So I can limit more of the magnetic field. If I'm pushing 1,000 megabits per second, I'm sending it at a faster rate. If I'm sending it at a faster rate, I'm going to be increasing the velocity. Increasing the velocity Increasing the bandwidth, it's going to cause me to have a bigger magnetic field around that wire. So I give it more twists per inch. Wait a minute, Kyle, are you telling me that I can actually take a Cat5 cable and just open it up and twist more cables and run 1 gigabits per second? Yeah, good luck. But yeah, you could do that. And it'll be fine. The pinouts are different on the 1 gigabits per second as well. So you gotta be careful of that. So when normally I would just hook the cables anywhere I want. And you think about this, if you have 4 cables, and 2 are transmit, and 2 are receive, you have to make sure that on the other side, they are the same. So whatever pin 1 is, and 2, and 3, and 6, because those really are the pins that you're going to be using, you have to make sure that whatever color this is on this side has to be the same color on this side. And that means you have a straight through cable. Now the interesting thing about this is you're going to be using the same pairs. So if this is the blue pair and this is the green pair, you're going to be making sure that you're not altering the pairs. I mean, you're not going to have a cable on this side. You're not going to have blue and then blue. I'm messing up completely today. You're not going to have blue, then blue stripe, and then green, and green. Actually, we'll say green and brown. These are not going to be your transmit, and these are going to be your receive. You want your color pairs to be a pair, which means if you're going to be transmitting, you're going to want to be transmitting on a pair that has a certain amount of twists per inch. You don't want to have a pair of receiving or transmitting wire where one of those wires is green and one of them is a total different pair sitting somewhere else. So I want you to think about this. This is what I used to do. I used to do my colors in order. And let's actually get to our cable pinouts anyway, since that's where we're kind of going to. So look at the colors that we have. These are our standard cables. Notice that I told you 1, 2, 3, and 6 are what we're using. 1 and 2 for transmit. Receive is 3 and 6. Now you can use whatever standard that you want. You can use A or B. Here's A right here, and B's down here, which is in this direction. But if we look at the actual pairs, notice that this and this, even though they're different, we skipped a couple pins, they're the same cable. Now, this is what I used to do back in the day when I used to make my cables, because I didn't really understand about the standards or the twist per inch or the magnetic fields. So this is what I would do. I would actually go in alphabetical order. So I will say blue, then blue stripe. I'm just going to leave that as a stripe. And then I would say, what's after blue? We have green. No, we have brown. Brown, then brown stripe. And then I will go to green, then green stripe, then orange stripe. I didn't want to have to remember all this when I was back, back in the day. So I just made my own, 1, 2, 3, 4, blue, brown, green, and orange. And let's see what happens. 1, 2, 3, 4, 5, 6, 7, 8. So these two are good. This one, let's look at this. This one, 3 and 6 are not. Now, everything worked fine. You know, I could have had problems, never really realized it. But this is how I used to hook up my cables when I used to create them. I used to do it all the time. Because I wasn't a cable guy. Now, this is nowhere near, I'm talking about back in the 90s, guys, when I used to make my own cables because it was fun and it was cool to actually create these. And whenever I needed a cable and didn't have one, I would create my own. So, this is not good. If you pay attention to your pinouts here. Not a good idea. Now, if I would have hooked up 1 gigabits per second and it used all the pairs, I want you to think about that. We're definitely going to have some communication problems. In fact, you probably won't get communication at all. Where this was okay. Well, let's think about that because maybe this was already doing its job, canceling out. Going down the brown wire and green wire as it was receiving, not that big of a deal. But remember, it might be receiving on this end, but on the other end, it's going to be doing what? It's going to be transmitting. Because if I'm receiving on this end and on this end, guess what's happening over here? It's being transmitted to me in this direction. So whatever this is plugged in on the side is going to be transmitted. So these standards, they're for a reason. If you want to create your own standard, that's fine. Just remember that these were chosen for a reason. And the reason was because of the fact of their magnetic field, their twists per inch. But the main thing is, as long as you have the 2 pairs, or have a pair that's doing the transmitting and the receiving, you'll be good to go. I've always done it that way back in the 90s, always had communication. Except when you try to do this with the gig, it's not going to work. And it's not a good idea to do it the way I used to do it. It's actually a bad idea if you want to get proper communication and not have any issues. So notice that these are a pair, and this is a pair. Sorry, I'm doing the wrong ones here. This and this is a pair. That orange and brown kind of look similar. Then I was like, well, I shouldn't be all the way down here. Okay, so these are what we call pinouts because as we plug these into our RJ45 jacks or our RJ45 plugs, the green wire is going to go to the pin 1. Pin 1 will always be on the left-hand side as the clip of the RJ45 plug or RJ45 end piece, which is plastic. The clip will always be facing down, and your pin 1 will always be to the left. Now, this concept is what we call a straight-through cable, right here. Because pin 1 is going to 1, 2 is going to 2, 3 is going to 3, 4, 5, 6, 7, and 8. And that's the way it's supposed to be. Now with this is what we call a crossover cable. The crossover cables are a necessity still today. So remember what I said about, obviously, you're going to have, if someone's transmitting on this side, they're going to be receiving on this side. Now this makes sense because if I actually take this down here, let's kind of, why don't we just bring up, no, we want to kind of leave it up here. Why not just move it all down? That'd be easier. Let's shrink it, select it all, and move it down. Apparently it doesn't want to move. So if I have a network card, sitting on this PC. And here's another PC. And I got these cables coming across. Now this will be my Cat 5, but let's say that for giggles, we just have this cable going, these 4 cables going across. Now on the one NIC card, I'm going to transmit out here. And I'm going to transmit out this one. Here I'm going to receive and receive. The way I like to explain this is like this. So let's do this a little bit better here. Let's make it a little bit bigger so we can have cables a little farther apart so I can actually write. This is going to be transmit, this is going to be transmit, this is going to be receive, this is going to be receive. And that's on this PC1 side. I like to think of communication as walkie-talkies. It's my button here, here's my speaker. Here's my antenna. Now, the nice thing about walkie-talkies is you can talk via a distance. But I want you to think about this. Here's Bob. Here's Tim. Now, Bob needs to speak to Tim. So Bob pushes this button. When he pushes this button, what he's doing is he's transmitting on this signal. Now, remember, this signal here, whatever it is, it's just a channel, a frequency, but we call it a channel. Which means if I put this one on channel 1, it's going to be on a certain frequency, and I put this on channel 1 on a certain frequency, they will be able to communicate. But when Bob pushes his button, he's going to send data out onto this channel. Tim's going to receive that data. But when Tim goes to speak, Tim's going to send data down that channel and Bob will receive it. Now, I need you to understand this. When Bob is sending traffic or sending data down this channel, Bob can only send the data. If he wants to listen to anything coming to him, he has to release. So they can only communicate or receive at one time. Now, this is called the real name is called half duplex. But that's not really the lesson we're talking about here. The real lesson is if these two pushes the button at the same time and they start communicating, there's no way. It's going to come in, they're going to collide. And the problem with this is neither one is going to be able to hear or talk at all. I mean, they can talk, but they definitely won't be able to hear anything coming in. So that means we have to understand something. In order for Bob to communicate with Tim, Tim has to have his finger off this button. And when he's having his finger off the button, what mode is he in? He's in receive mode. That's what mode he's in. He's ready to receive the data or the transmission. When he's pushing this button, he is then transmitting. So in order for this, the only way for this communication to be successful is when Bob pushes this button, and while he is transmitting, Tim is receiving. Does that make sense? So while Bob is transmitting, Tim must be receiving. When Tim is transmitting, Bob must be receiving. This is very important to understand because it makes sense. If Bob decides to transmit while Tim is transmitting, how's that possible? It's not going to work. It's like pushing water outside on one side of the pipe, of a water pipe, and pushing it on the other side as well. So let's think about this. We have a faucet here. Water comes shooting out. Now, we tie this hose to it. This hose comes out. This hose comes out to this end. And water comes shooting out. Now, what happens if I decide to take another faucet and tie a hose to that and connect it to this? Well, you got two sides pushing the water out, but it's not coming out of anywhere. Does that kind of make sense? You're colliding the water. It has nowhere to go. It just, pressure builds up and it just sits there. That's it. Although we're not talking about pressure and don't care about pressure, the bottom line is it has nowhere to go. So if this PC sitting over here was set up like this as well, which it is, the same network card that's in this PC is set up the same way as PC2. That causes a problem. Because PC1, when it transmits, guess where it's going to be sending its data? It's going to be sending down this pin, this cable number 1. And PC, when he tries to transmit, cable number 1. And guess what happens? They collide. It's impossible for this communication to happen. PC1 or PC2 would have to have it set up like this. Receive, transmit. Now, does this make sense? Because now when PC is transmitting, guess what PC2 is doing? He's getting PC1's wire or transmission on his receiving end. That makes sense. But remember, these network cards are all built the same. So we can't just, I mean, the only way to do this is really to go into the network card and actually change the pins around with circuitry and stuff like that, or we can be a little bit less hardcore like that and change our cables. Because we know this is transmit, this is transmit, this is receive, and this is receive. So instead of us going in and trying to make changes to the network card, leave the network card the same. And let's take our cable here. And let's take one of these transmits and bring it over to one of the receives. One of the transmits, bring it over to the receive. Then we take one of our receives, bring it over to the transmit. One of our receives, bring it over to the transmit. Now this makes sense. Now one of the things you also have to realize is this. I'm dealing with electricity. So since I'm dealing with electricity, what do we need for electricity to work? Positive and negative charges. So as you can see, this is why I have two transmitting cables. One's positive and one's negative. Receive, one's positive, one negative. Now the problem with this is, remember what happens if you take a negative charge and tie it to a positive charge. Now if you don't know this, that's fine. You know, I know this from my electrician days, and of course when you learn physics, you learn this as well. Okay, when you take a negative charge and tie it to a positive charge, what happens? It gets discharged. Whatever this is gets discharged, it shorts out, and you're done. So you got to make sure that your negative stays with your negative and your positive stays with your positive. Now, you can remember all this, get out your meter, try to figure out all this stuff is, or you could just remember the sequence. If this is pin 1, and this is pin 2, and this is pin 3, and this is pin 6, what are these? 1, 2, 3, and 6, right? So as you can see, 1 is going to 3 and 2 is going to 6. If you just remember that, 1 to 3 and 2 to 6, you will be able to make your crossover cable. These are the only two you have to remember. 1 to 3, 2 to 6. 1 to 3, 2 to 6. 1 to 3, 2 to 6. You don't need to remember 1 to 3, 2 to 6, 3 to 1, 6 to 2. That kind of gets, a little bit too much. If you want to memorize it that way, that's fine. But 1 to 3, 2 to 6. That's all I remember. I know on this side is 1 to 3, 2 to 6, and on this side is 1 to 3, 2 to 6. And now, because you have done this, you have crossed the cables from the transmitting side over to the receive side on the other end. Because remember, you're going to have a long cable here. You're going to have your RJ45 sitting here. You have this nice little thing going across. The cable's going to come out of it. It's going to be a nice long cable. In here, you're going to have your RJ45s, and you got these pins sitting here. Okay? And on the other side of this cable, guess what you're going to have? Well, the same thing. So you got to make sure whatever's sitting on this pin, on pin 1, needs to be on what? Pin 3 over here. Whatever cable you're using. If you're using the green stripe here on pin 1, that green stripe over here needs to be on pin 3. Does that make sense? This will be going to pin 3. And you would do this with each one of these cables. This is what we call a crossover cable. Does this mean that you need to learn how to make crossover cables? No. Should you? Oh, absolutely. You should go out there and get yourself a cheap pair of crimps and make some cables, man. Doesn't matter if they're perfect. Doesn't matter if you cut them really long, and just do it to see how it works and see if it does work. So that makes me wonder then, because do I buy crossover cables for everything? Well, that's an interesting thing. Let's talk about that. Let's take a look at our PC here. I'm going to draw a big one this time. And let's take a look at our switch. Okay, so here's port 1, and here's port 2. I'm not going to draw the rest of the ports. This will be switch 1. Going into the switch port, I'm going to have an Ethernet cable, which means I'm going to have 4 cables. Technically 8, but we're only going to be drawing the 4. Coming from one network card to the other. I'm going to have, coming out of my PC, I'm going to have pin 1, 2, 3, 4. This is going to be 1, 2, 3, sorry, not 4, 6. 1, 2, 3, and 6 are going to be the pins that I'm using to do my communication. Now, PC 1, he's going to have transmission up here, transmission. We all know this. This is how all the network cards are with the PCs. He's going to have receive and receive. Now, I can even add the plus and the minus and the plus and the minus if I want to. But, however, do we use crossover cables going from a PC to a switch? No. We use a straight-through cable. Interesting. Now, if that's based on what you just told me, Kyle, is that means that if that's the case, there's no way this switch port, it's like your normal Ethernet ports. I mean, it's still an Ethernet port, but there's no way this communication happens unless this is a receive and this is a transmit. So pretty much, if I understood what you stated before, that means 1 and 2 from a switch will be receiving, and 3 and 6 will be transmitting. And that's exactly what will happen. That's why you can plug a straight-through cable into this switch. So that means your switch pinouts are different than your PC pinouts. Pretty cool. And that's how, now you're starting to get an understanding how these cables plugging into these devices, how they work. Do you need to know this? Absolutely. You don't need to know it to this granular degree as far as a transmit receive, but you need to know what a straight through cable is and what a crossover cable is. It is important. The problem is when we explain these things, we just go through it quickly, and that's it. And that's what is really important for you to understand exactly why we need crossover cables and why we use straight through cable. So far so cool. So that means if I am connecting 2 devices that have the same pinouts, what do I need? A crossover cable. If I have 2 PCs that have different pinouts that are relevant to my pinouts, now that's really important because I can plug this cable, this PC network card into a console cable, but it doesn't mean it's relevant. I mean, the jack might plug in, but it doesn't mean those pinouts are relevant to the point where I can transmit and receive and get data from it. You see my point? So plugging a PC into a switch goes together. I mean, it's like bread and butter, right? They go together. So if it's like bread and butter, obviously this pinout and this pinout have relations in some way, shape, or form, which means they're opposite, so those 2 can communicate. Now that we know what a crossover is used for, and we know the necessity for a crossover and a straight-through cable, we now know that all switches are set up to the fact that we can actually use PCs to connect to those switches with straight-through cables. Now, this is good to understand because we have to have some type of sense of when do we need a crossover cable and when we don't need the crossover cable. And really all this down here is really just showing you the different types of pairs that we can use. Here's a standard A, here's a standard B. But as you can see, it's still the same concept. Still 1 and 2 are pairs. 3 and 6 are pairs. Here's our crossover cables. When we're just using 100 megabits per second. And here's our cabling when we're actually using 1 gig. Notice that we're using all 8 cables instead of just 4. So you mess up this type of communication, things they're just not going to work right. So let's look at what happens when we have a certain device. Now, eventually you're going to learn the different types of devices that we have here. You're going to learn that our routers are layer 3 devices, which you're going to learn later on. You're going to learn that our switches are layer 2 devices. You're going to learn that our network cards are layer 3 devices. Our bridges are layer 2 devices, which you're not going to really get in detail with that. And you're also going to learn, which actually that's what we're just discussing now, that hubs are layer 1. Hubs are layer 1 because we don't use MAC addresses. So the fact that this says layer 2 is not correct. It's actually a layer 1 device. Now, as far as the bridge is concerned, we won't really be bringing that up again or the hub again, and most likely, but we'll be talking about layer 3 and layer 2 devices all the time. Nonetheless, the interesting thing is when we are connecting a router to a switch. Remember, the normal way to do this is pin 1 and 2 will be transmitting. While pin 1 and 2 on a switch is receiving. So anytime you're plugging into a switch, a straight through cable would do just fine. Again, the key factor is you're going to need a crossover cable when the pins are matching up to be the same. So pin 1 and 2 are transmit on this side, and over here, pin 1 and 2 are transmitting. Yeah, you're going to need a crossover cable, right? But knowing what we know about a switch, we should be good to go. We can use a straight through cable here. Not a big deal. Not a big deal at all. PC going to a switch, pins 1 and 2 will be used here. So, no big deal. This will be a straight through cable. Now, if the switch, if their pin 1 and 2 are receive, don't you think the other side, if you're plugging into a switch, pin 1 and 2 will also be receiving? So, you would need a crossover cable here. If a router, pin 1 and 2 are transmit, don't you think the other side of a router port will be 1 and 2 will be transmitting? So that means you're going to need a crossover cable here. Starting to make sense? I think I lost my mouse there. Let's scroll this down. Hub to hub, yeah, you're going to need a crossover cable. I mean, you got to, somewhat common sense will be used here saying, okay, well, if I got 2 like devices, obviously I'm connecting a hub and a hub, a router and a router, a PC and PC. Obviously, the pins are going to be exactly the same. I'm going to have a crossover cable there. But a hub also has pin 1 and 2 as received. So having a PC plugged into it is no big deal. We can use a straight through cable. Hub and switch, both of their pins are received on pin 1 and 2. So we're going to need a crossover cable. And going from a PC to a router, this is one of the most important things because it's very easy to plug a PC into a router or a server into a router and forget that their network cards both have 1 and 2, transmitting. So because of that, we will need a crossover cable. So all the information we were talking about before, it gives you a better understanding of why these crossovers are needed, not just memorizing what needs to be done. Okay? So let's talk about a little bit more fundamentals here. One of them is, what is an IP address? We're not going to get really detailed in addressing at this moment, but an IP address is an identifier. And that's all it is. It is a number that is used to identify a device on the network. So what does that mean? That means every PC, every printer, every wireless device, no matter what, if it needs to communicate with each other, it needs an IP address. So that means if I have a communication like so, this is going to have an IP address. This is going to have an IP address right here. Even my switch can have an IP address, but as I'm moving data from here to here, I'm not using IP to move that data. I'm not using IP addresses. So at this point, think of a switch as no IP addresses. Think of this as a underlayer passageway for my IP addresses at this moment. Switches work on what we call layer 2. Routers work on layer 3. And of course, your PCs, its net card will be layer 3. So think of that traffic leaving PC, layer 3 information coming into this switch. Think of that traffic leaving PC, layer 3 information coming into this switch. This switch is going to move the data to layer 2 and move it up through here to go back to layer 3. Now, you'll have a better understanding about this when we go into, it's either going to be the next section or the next section after that when we talk about the OSI model. So let's talk about an IP address. What does it look like? An IP address has 4 digits. 4 sets of numbers, I should say, not 4 digits, but 4 sets of numbers. Now, I have to tell you, this is IP version 4. Version 6 is a lot different, but we're going to focus on IP version 4. We have 4 different sets of numbers. Each one of these numbers can be anywhere from 0 to 255, except this number. This number here, this first digit, can have a range between 1 to 255. All these, the rest of them, can have 0 to 255. So you will see a number similar to this. 192.168.1.1. This is an IP address. Notice this is within our range, 1 to 255. So you would never see a number like 192, 256, 358, 300. This is an invalid number for this section. This is invalid, and this is invalid. You can't have these numbers more than 255. You'll find out later why that is, but at this point, just remember that this is the basics of an IP address. You have 4 digits. So in these 4 digits, you have what is called a network number and a host number. For now, think of the network number as your network A, network B. So if I had a network number of 192.168.1.0, this is telling me this is the network that I belong to. My network numbers are going to be 1, 168, 192, or 192.168.1. We do read it from left to right. If I had a number of 192.168.1.1, that means this is really the host number. So that's interesting because that means every PC, every router, everything that has an IP address will have a network number and one number that identifies them on that network. So if we're on the 192.168.1 network, if I gave this IP address to here, he will be number 1 on that network. If I gave this a 192.168.1.27, okay, he will be number 27 of the 192.168.1 network. Host means PC, printer, whatever you also want to call it. It also means node. Good to know. So that's what an IP address is. So what is a MAC address? Now, before we talk about MAC addresses, remember IP addresses is a layer 3 concept. And believe me, you will be reminded of this on a regular basis. So what is a MAC address? A MAC address is set up with these interesting numbers here. A, B, C, D, E, F, 1, 2, 3, 4, 5, 6. Each one of these digits, notice that we have how many numbers there, if we count them all. 2, 4, 6, 8, 10, 12. We have 12 numbers. And each one of these digits can have a value of 0 to 9 or A through F. Now, what is this A through F? This is what we call hexadecimal. Hexadecimal is a way of writing this in a way where we can use numbers and letters. The idea of this is we want to have the ability to have a way of each one of these digits having a range of 15, which means it could be 15 different values. Now, how can I actually have 15 different values if after I get to the digit 9, I can't write 10 as a 1 digit? I just can't. Can't be done. Now, the nice thing about it is, if I want to write a 10, I will use the letter A. 11 will be B, 12 will be C, 13 will be D, 14 will be E, and 15 will be F. So you would never see in a hexadecimal value, as far as our MAC addresses are concerned, you would never see anything higher than an F, and you would see anything that's 0 through 9. So if I look at my MAC address here on my PC, let's take a look at it. Here's an interesting MAC address number, 0026188200B1. Every network card has a MAC address. IP addresses is what you assign yourself, but the MAC addresses are already on the network cards when you buy them. Now, because of this allows a switch to create a table with all the MAC addresses that are communicating on this. That means this PC has an IP address and a MAC address. If the MAC address is A, B, C, D, we're going to write like this because this is how Cisco writes it. E, F, 1, 2, 3, 4, 5, 6. All right, I'm going to have a little trouble here. 3, 4, 5, 6. If this is the MAC address number of this PC, then when PC sends the data and trying to reach over here to router 1, this switch will record this MAC address and put it in this MAC table. And there it will sit. And it will say, look, this MAC address of A, B, C, D, .x, whatever, matches to port, we'll say it's port, we'll just say this is port 1 of the switch. Matches to port 1. So now anytime data is being sent into this switch and needs to reach this MAC address, it will automatically look in this table and say, oh, I know where that MAC address is sitting. It's sitting on this port. Let's send it out. So we can forward data by MAC addresses. That's the job of a switch. So now you've learned that a router will actually send data based on IP addresses, which sits at layer 3, and switches will move data through the switch and send it out another interface based on the MAC address. And that's what we call layer 2. So that's why I said that when this traffic is leaving this PC, it's leaving as a layer 3 information. It comes into the switch. This switch will forward this information via layer 2. That data will go out here as layer 2 information. This router will will look at this information, look at the layer 3 information, and forward it on based on the destination IP address, or the IP address that we're trying to go to. Interesting. But this is what happens. And trust me, we'll get more and more deep in this. But this is the basics for right now. So that means we have two major components. We have an IP address, and we have a MAC address. Now, one thing you need to understand, since we're learning these two things now, and what they are, really we're just learning the formats of them, how do they look, and what they're used for. A PC must have both to communicate. Which means, when PC 1 communicates with PC 2, in order for this communication to work, PC 1 must have the MAC address and IP address that he wants to communicate with. So if this is an IP address of 192.168.1.1, and this is 192.168.1.2, PC1 says, I want to try to communicate with 192.168.1.2, and he must have the PC's MAC address as well. And this is the MAC address that I want to communicate with. Assuming that's the MAC address of PC2. So in order for communication to happen, we must have an IP address. We must have a MAC address. MAC addresses are easy. They're already on the network card. Hey, that was pretty easy for you. The IP addresses are what we actually define ourselves and what we assign. So what does it mean now, after all this? What does it mean to be on the same network? Well, let's talk about that. I originally said that 192.168.1 for my previous example was my network number. So I will write this out as 192.168.1.0. I'm not going to put a 0 there. I'm just going to put an X. So this is my network number. These are my networks. This is my host. If this was my network number, then this was my host, let's understand what that really means. So you're going to have two parts of an IP address. The network and the host. Now the host is whatever is not the network. Does that make sense? So if my network was 192.168, then this would be my host. Now, based on the IP address that we're using now, you would never see this fashion. But again, if we could do this with the 192 address, then that's what you would see. Anything that's not the network or host. At this point, we have 3 of the numbers that are our network number, and only one of them a host. And each one of these numbers cannot go higher than 255. And if we actually use 0 as a network number, then obviously I have a value of 1 to 254. And you'll understand this later on. Why is only 254? We could have a 255 that we can actually ping to. We just couldn't put it on an interface. And there's a reason for that, which you'll learn later on as well. So what does it mean to be on the same network? That means anyone that has this same exact numbers as the network portion of the IP address will be able to communicate. So if I have a host with a 192.168.1 network, I'll put the other number in there later on, and a 192.168.1 we'll make this 10, we'll make this 5. Well, the question is, with PC1 and PC2, are their network numbers the same? 192.168.1, 192.168.1, they are the same, so they're on the same network. This is the 5th host, this is the 10th host. And not because we put them in order, it's just the fact that that's just number 10. Does that make sense? So think about this as an address perspective. You live at 123 Fake Street. At Nowhere, Virginia. Okay? Nowhere, Virginia. Let's just write Nowhere, VA. No point in writing it all out. Nowhere, VA. 20121. Okay? Think of this as your network. Think about it. Anyone who lives at this particular address can communicate with each other, right? My name is Kyle. That's my host name. That's who I am. Okay? If Bob was living with me, Bob would also have an identifier. His identifier is Bob. So when Kyle needs to communicate with Bob, he will call out, "Hey, Bob." With PC2, when he's trying to communicate with, when PC1, he's trying to communicate with PC2, guess what he's going to say? "Hey, 10, how you doing? Let's chat." But he's not going to say, "Hey, 10. He's going to say, "Hey, 192.168.1.10. How you doing?" Now, if I put this as a 2, these networks are not the same. 192.168.2, that's the network. And 192.168.1, they're not the same. 192.168.1, 192.168.2. not the same network. Therefore, if our network numbers are different, there's no communication. They're not going to be able to communicate with each other. This is what it means to be on the same network. And we already talked about bits, and kilobits, and megabits, and gigabits. And that's pretty much it for the network fundamentals. This is really giving you a decent understanding of the basics of the network fundamentals. We still got 3 more chapters to go through. But as far as this is concerned, this chapter really gets involved with explaining the basics of what a network is. That was really what this chapter's about. What does it mean? What are these terms that we're going to use? How do we, what is it? How do they all fit together? What does it all mean? And that's pretty much it with this particular course as far as this chapter 1. And I will see you at chapter